Okay, let's dive right into this. We are going on a journey today, a pretty intense cosmic journey into one of the absolute most fascinating and yet kind of terrifying phenomena in the universe. Welcome to The Explainer.
Right off the bat, here's the big question. What actually happens if you fall into a black hole? It's a wild thought experiment, right? I want you to picture yourself as the main character here. Imagine you're just floating out there, totally alone in the deep, dark expanse of space, and you're drifting closer and closer to this absolute cosmic abyss. What would you see? How would you experience time? What would literally happen to your body? Well, to figure all that out, we've got to understand the physics of where we're heading.
So, Section 1. What is a black hole?
Before we take the plunge, let's get the basics down. In simplest terms, a black hole is just a massive amount of stuff compressed into a ridiculously tiny space. Mathematically, it's all about this thing called the Schwarzschild Radius. Basically, every single object has this state. If you squeeze something so hard that you actually remove all the empty space between its atoms, its density just skyrockets. It creates a gravitational pull so intense, curving space-time so drastically that absolutely nothing, not even photons, literally the fastest particles of light, can escape.
And this brilliantly illustrates just how crazy the math of our universe is. Seriously, anything has the theoretical potential to become a black hole if it's squeezed down to its Schwarzschild radius. You, me, the phone in your pocket, our entire planet. Like if we could magically squish the Earth down to the size of a tiny marble, getting rid of all that empty atomic space, boom, it becomes a black hole.
Moving on to Section 2, the death of a star.
Now, obviously, there are no giant cosmic hands out there squishing planets into marbles. So how do these massive beasts actually form in reality? Well, it starts with the death of a huge star. A massive star is basically trapped in a lifelong tug-of-war. On one side, you've got gravity, relentlessly pulling all the star's mass inward. But on the other side, you have nuclear fusion. The star's core is this gigantic engine smashing hydrogen atoms into helium, which releases a massive amount of energy pushing outward. As long as the inward pull of gravity and the outward push of that radiation are perfectly balanced, the star survives.
Let's see how this builds up to a complete catastrophe. These massive stars burn fast. They fuse hydrogen, then helium, and keep fusing heavier and heavier elements in their core. But then, they hit iron. When atoms fuse to make iron, it suddenly doesn't release energy anymore. The outward push just completely stops. The balance is shattered. And in a fraction of a second, gravity wins. The entire core implodes under its own massive weight, creating such intense heat and pressure that it forges all the heavy elements in the universe. If the star's remains are massive enough, it just collapses endlessly into a black hole.
All right, the beast is born. Section 3. Anatomy of a black hole.
Before we jump in, let's look at the map so we know what we're actually dealing with here. The first major landmark is the event horizon. When you see a picture of a black hole, this is the black part. It is the absolute outer boundary, the point of no return. Once you cross this invisible line, gravity is so overwhelming that to escape, you'd have to travel faster than the speed of light, which, as we know, is completely impossible. Our one-way trip inward really kicks off right here. Then right at the very center, you have the singularity. If the event horizon is the black, the singularity is the actual hole. All that mass from the dead star is crushed into a single point. According to the math we have right now, the density there is literally infinite. But, and this is a big but, science still considers this a profound mystery. We honestly just don't know exactly what exists there, because our standard laws of physics completely break down at that point.
Okay, you know the anatomy. Section 4. Bending light and time.
Let's step off the ledge. As I guide you across the event horizon, get ready for things to get really weird. As you get closer, the sky around you starts doing impossible things. Because the gravity is literally warping the geometry of space and time, it acts like a giant, bizarre cosmic magnifying glass. Say there was a bright blue galaxy sitting directly behind the black hole. The gravity would stretch and curve that background light so much that the galaxy would look like a glowing ring wrapping all the way around the dark sphere.
You keep falling and the distortion gets even more extreme. Your field of view actually starts turning dark. Then you hit a layer called the Photon Sphere. This is a super unique zone where the gravity is so precisely balanced that particles of light, photons, are caught in a perfect loop. They aren't pulled all the way in yet, but they can't escape either. They just endlessly orbit the black hole.
Now, what's really interesting about this concept is what happens to your vision.
Think about it, because light is traveling in circles around the black hole right next to you, light that bounces off the back of your head could travel all the way around the black hole and hit your own eyes. So if you just turned your head sideways, you could literally gaze at the back of your own head. How incredibly surreal is that?
But wait, it's not just space and light getting warped, it's time itself. If a friend was safely watching you fall from a spaceship far away, they wouldn't see you just zip into the dark. To them, time around you is slowing down. You'd look like you were falling slower and slower. The light coming from you would stretch out, turning you red, until you just fade away completely. But for you, time feels totally normal. You just look back out and watch the entire outside universe shrink down into this tiny, smaller and smaller circle of light as the darkness completely swallows you.
You're deep inside now. Section 5. The Spaghettification effect.
We gotta brace ourselves for the, well, fatal climax of our journey. As you approach the center, the gravity intensifies at a frankly terrifying rate. So, the crucial point here is that gravity becomes drastically different even across very tiny distances. If you're falling feet first, the gravitational pull on your feet will quickly become millions of times stronger than the pull on your head.
And that extreme difference? It leads to a grisly process that astrophysicists literally call spaghettification. I mean, it sounds kind of funny, but it's brutal. That immense force physically rips you apart, stretching all the atoms of your body into a single long straight line, like a piece of cosmic spaghetti. You'd be utterly dismantled right before those constituent atoms finally get pulled into the infinitely dense singularity.
Okay, let's take a deep breath. Let's ground ourselves back in safety for a second. Our thought experiment obviously had a pretty brutal ending, but I wanted to spell a huge myth right now. Black holes are not giant cosmic vacuum cleaners just actively sucking up the universe. Their gravity works just like anything else with mass. You have to get incredibly close to actually fall in. For example, if we swapped our sun for a black hole of the exact same mass, the Earth wouldn't get sucked in. We'd just keep orbiting safely in the dark. So from a distance, we are totally fine.
We've covered the birth of these massive beasts, the mind-bending visual illusions, and well, the absolute destruction of falling in. But I want to leave you pondering our final destination, the singularity. If everything we know about the laws of physics just completely breaks down at that exact point of infinite density, what new realities might exist at the very center? Could it be a gateway to somewhere else? A dead end of compressed time? The truth is still waiting out there in the dark. Thanks for joining me on this explainer. Keep wondering, keep asking questions, and I'll see you next time.